Hello. How's everyone doing? All three people. You can go ahead and, if you have a QR scanner, you can scan this to sign in, um, or the moderator, Kwong, will post a link to the sign-in form if that's more convenient for you. And Kwong, I don't believe it pastes the link. All right, we're going to start in like 1 minute. And in the chat, if you can see the chat, oh, live chat. There we go, should do that. Then there is a link for the sign-in sheet. All right, so we will begin very shortly. All right. So let's begin. So, oops, that is the wrong place. Let me go one moment to... Okay, so in the description, again, there is the link for... there's a link for the download of the PCB workshop, and included in it, like I said previously, is 3 project files. There's a README if you want more information on how to actually do that part. So, what we're actually doing today is starting at the first one because we are doing the PCB design. So as you can see, we have our final design here. And if we look at the actual PCB news section, then you can see it does not have the schematic or the PCB design laid out, but it does have, some useful shortcuts and best practices. So, like I said previously, the top of the bar here is kind of like a list of steps if you think about it. You start at the left, you do the edit page settings. These aren't really part of that list that I'm referring to. It's just printing and zooming and things, which you don't usually touch other than printing out the schematic design as a PDF. If you're curious about how to do that, you would just click print and then choose to the right. You have print to PDF, and then you can print the design. And that's how I printed the reference that is in the 0th project file for you to design the schematic. So you skip these, and obviously the navigate schematic hierarchy, which I talked about. So now, the first step is create and edit symbols for this schematic, which we did, and I explained how to do. Browse symbol libraries, you can browse all the libraries for the symbols. And now we have the footprint editor. Now, just a quick explanation. Symbols are what are used in the schematic, and footprints are what are used in the PCB design. So these are symbols right here, and the footprint is actually the physical, like pads and things that are actually going on the design. So most, pre-selected things have, footprints associated with them. For example, this right here, if I press E on it, it does already have a footprint assigned to it. But my LED clock display, which I made, as you can see, does not have a footprint assigned to it. And just a reminder, on the left I have the buttons that I'm pressing in case you want a reference visually. Okay, so we have to start actually making the footprints that are related to the LED clock display and the micro USB breakout board. So to do that, you come up here to the footprint editor and just click that. And now, the same as making a symbol, you can think of the process as very similar. We first have to create a library for our project, so I'm going to go ahead and click New Library. It'll default to the main file folder that your project is located in, and we're just going to call this here. I kind of want to use that name, New Library, the default name. So I'm just going to do IEEE underscore at mega 320p underscore footprints. I'm going to click Save. And I'm going to make this project based. If it's global, then you can share the same library within the various different projects that you may have, which is also a useful thing to do if you have various projects that use the same components. So you can go ahead and click OK, and it will load. And I am sorry, this process takes forever. I have an SSD, yet I couldn't tell you why it takes so long. It's probably because my hard drive is so full. I probably should start do a factory reset or something. So just bear in mind that it'll take a bit. And this part right at the end takes forever. So I will awkwardly wait. Let me check the chat. No one's said anything. Just a quick reminder. In the chat there's a sign-in link, so go ahead and do that. All right. So we just created our library. So if we type IEEE underscore, you can see our new empty library has been created. And this is a libraries right here. So you can click that and then right click it and then click Create Footprint from Wizard. Now you have two different ways of creating footprints. You first have to look at the datasheet of whatever you're actually trying to create the footprint of and see, all right, is this kind of a standard, is this kind of a standard footprint, or is it really weird to where I need to make like a custom thing? And as you can see, this right here is a PDIP. It's it's a dual inline through hole component where it has rows and columns of pins that are 2.54 millimeters separated. So I know that in order to make a PDIP component, I can right click and click create new component from Wizard, and then you have this window that pops up called footprint generators. And you have various different types of footprints. You have circular pad arrays, quad flat no lead footprints. SDIP is what we're actually going to use. SOIC, touch slider, zip. Various different types of footprints. So we're actually going to use this SDIP, which is dual inline package footprint wizard. So go ahead and click that, and as you can see, it kind of generates this thing for us. And on the left here, we have a list of parameters. So the pad count, if you look at that is my schedule. If you look at this, you can see it has 1, 2, 3, 4, 5, 6, 7 times 2, 14 separate pads. So I can come here, and I can type 14 here, and now it switches to 14. What's not standard about this is, as you can see, the distance between the two rows. This is the side view from this direction. You can see it's 15.24 millimeters across. So yeah, what I'm going to do is go in here to the row spacing, which is the spacing between all of the rows, and these separate things are columns. So these two are rows, and the row spacing, let me remind myself, 15.24 millimeters. So I can come here, 15.24 millimeters, press enter, and now you can see it is very similar. And various other parameters you have are, you can see 2.54 times 6. That means that the distance between these pads is 2.54, and there is 6 times those distances, which produces 7 pins. So that tells you that the distance between two separate pins is 2.54 millimeters. And when you come to the wizard here, you can see that that's referring to the pad pitch. And it's already defaulted because 2.54 millimeters is a standard value. So I believe now we are good. Another thing to look at possibly is if you look here, it's kind of hard to tell, but this right here, you could see it kind of has two arrows pointing, and it kind of tells you the distance, but it's essentially the size of the pins. So what we can do there is, that was 0.5 millimeters, and our drill size refers to how big the holes are. That's 0.8. We're just going to keep it like that to give it some room. When you solder it on the board, it'll make a good connection, so you don't have to worry about the few, small differences between the drill size and the pin size. And then you have the pad width and pad length. That refers to the pad's actual size. So you can see that the width is 1.2 millimeters and the length is 2 millimeters. If I wanted it to be perfectly circular, I can make the width 2 as well, and now you can see it's circular. But I'm just going to keep it at 1.2 because I think it reduces the chance of, accidentally making a connection between two pins, which is their thinking into changing kind of how the pad sizes are. And obviously, you can increase the row count and the row spacing, which we did. So yeah, so there's that. So now we're happy with this, right? So what you can do after doing a wizard, creating something through the wizard, you can come up here and click Export Footprint to Editor. All right, and so now you can see our library contains this kind of defaulted, PDIP component, but we do need to change some things. So first, what we're going to do is actually click Save As, and we're going to name it something else. I'm just going to call it LED Clock Display, and I'm going to save it into that thing right there. So it makes a copy, so I'm just going to come up here and actually delete this one. Delete that one, because that is the incorrect name. So now you can see this, this field right here is the correct name. So now what I'm actually going to do is talk about a few important things. What we're actually in right now is an editor that's very similar to the actual PCB Design editor. So all these layers right here in the Layers Manager, that actually corresponds to all the layers that you have anyways. What we actually have to do is work with the silk layer. And the silk layer is essentially the layer on the PCB that you can create graphics that whoever is assembling the component, they can actually see those graphics. So as you can see, the silk layer, if I turn it on and off, you can see that this is the silk layer. You can see it's just this kind of square that has like an indentation. And if I click View 3D Viewer, you can see that the silk layer shows up as kind of a white, graphic. And also it actually shows the reference designator. So I'm just going to rotate that and put that there. And REF asterisk asterisk, that's actually a it's kind of a filler function that the software, when it actually puts the PCB footprint onto the PCB Design editor, it'll actually know that this should be replaced with the reference designator and its number. So like if you have resistor 1, this would be changed to resistor 1, R1. So there's that. And that's just on the silk mask. So when you're actually editing the PCB, you can actually see which component that is, which is very important for the person who's actually designing the component. So now, or actually assembling the PCB. Okay, sorry about that. So this right here is too small, in my opinion, because I personally believe it would be best to show the person who's assembling it how big the component is, like how big the actual size of the component. And as you can see, the LED like structure is actually much bigger than the pins. So what I'm actually going to do is change the silk screen to actually show that this shape right here. So what I'm actually going to do is delete the current silk screen that exists. So I'm just going to zoom up, click on it, and press delete. Just do that really quickly. All right. And the top one right here. And I'm also going to delete this one right here, and I'll explain what that is as well. Delete that. Okay, so now I deleted both the silk screen and also the courtyard. And I'll explain what a courtyard is right after I explain how to make the silk screen. Okay, so what we need to do is kind of make it match these dimensions. And now I'm actually going to teach you a very, very important thing to learn, and that is using a grid to your advantage. So let's go ahead and edit the user grid. And with the user grid, you can actually set the origin. If you see right here, the origin is at 0, 0 right now, which is the center. But to make it easier for us to actually draw that silk screen, the thing that is showing the builder like the boundaries of the component, I'm actually going to change these settings to make it very easy for me to do so. So as you can see, the component is 50.2 millimeters wide, and it is 19 millimeters tall. So what I can do is I'm actually going to set the origin to minus half of the x distance. So that's minus 25.1 millimeters, which is half of 50.2. And the y, I'm going to set that to negative 9.5, which is half of 19. So I click that, and as you can see, now the origin is to the left here, and that's actually the top left corner of our component's boundary. And if we continue doing some settings, we can see, all right, what is an easy thing to do? If I go back to here, you could see that, this changes every zero. If I make it to 0.2 millimeters, the distance that the mouse actually moves every time you move it. If I change that to 0.2 millimeters, then it'll make it very easy to go from the top left to 50.2 millimeters. And as you can see, the y-axis, it's a whole number. It's 19. So I don't need it to be any more precise than that. So I will define the grid as being 1 millimeter. So if I click OK and actually select the user grid, then you can see that every time I move the mouse, it kind of jumps. If you look down at the bottom right here, it kind of jumps by 1, right? And if I go to the left and right, it jumps by 0.2. And that's very good. So what I'm going to do is just start at the origin. I'm going to select the silk screen, start at the origin. I'm going to actually choose Add Graphic Line. So I'm going to choose that. All right. And then I'm going to hold Control to keep it straight. And I will go down exactly. If you look on dy, I want the dy to change by 19 millimeters. If you look at the bottom right. So now you can see it is down 19 millimeters. And on the bottom right, if you see dx, I want that to be 50.2. And I'm holding Control, as you can see on the bottom left. I'm holding Control, and I want that to be 50.2. So I will click that. Now I'm coming up, and that has to be dy of negative 19. And then I'm going to the left, and that's a dx of negative 50.2. And that's going to go right back to the origin. And if I just go here and click one more time, it finishes it out. All right, so this is the boundary of our LED display. And now what we actually have to define is the courtyard. Now what a courtyard is it basically says no other components can be contained within this courtyard. We don't want resistors under our display because that could cause issues with assembly. So I'm just going to make the courtyard literally the exact same thing. So this is actually for design process. So if you have components that are overlapping, it'll produce an error in the design rules check. So that's the use of that. So I'm just going to go ahead and define this, negative 19, and we're going to go back to the origin. All right. So as you can see, if I delete that, we still have the silk screen in the back. So now if I click View 3D Viewer, you can see now the courtyard is pretty nice. And it is defined based on the, you know, the size of our display. So now this is complete. So now I'm going to go ahead and click Save. And I have one more footprint to create, and that is a 5-pin header, which is very basic. So what I'm going to have to do is to create footprint from Wizard. I'm going to do an S-dip, and I want it to be only one row, and I want it to be 5. And this is a 5-pin header. And the reason for that is because I have an adapter, which I'll show you real quick. As you can see, it takes a 5-pin header, and it's basically a micro USB breakout board. Micro USBs are usually hard. It requires like a reflow type of assembly, and it's just more complicated than I'm willing to do. So I'm just going to do a basic header. So I just created a pin header, and headers are the standard size, sizes. So the pad pitch will be the standard 2.54 millimeters, and everything else should be default. So I'm just going to go ahead and export that one as well, and I'll just keep it as SIP-5. I'll just keep it like that for now. And we are done creating our components, or footprints. All right, so let's go back to KiCAD. So now that we created our custom footprints, and by the way, just a note, all of these, basic components like capacitor and oscillator and resistor, there's like a lot of predefined footprints, and you would essentially match footprints based on the size and dimensions of whatever, component that you're actually trying to buy. And I'll show you that process. Let me first, so we did the schematic symbols, we did an electrical rules check, and now we have to click this button right here. And like I said, this is a list of steps. We did these two, and now we do the assign PCB footprints to schematic symbols. So I'm just gonna, oops, did I assign PCB footprints? Oh yeah, it tells me I have to first annotate my schematics symbols, so I did that, and now it's annotated, and what that does is it kind of fills in all of these question marks, like I said previously. Electrical rules check, I did that. I explained why these aren't really that big of a problem. And now we're going to assign footprints to our PCB. So what we can do is wait a bit, and it'll actually load this menu. And like I said, I press this button, assign PCB footprints to schematic symbols. So it loads this menu, and it has various things that you can put. The battery one, you could just go through and match all of these to whatever you have. Like I said, these are built into KiCAD. So, for my battery, I'm going to use battery holder Keystone 1060. As you can see, that's the one that I used for there. That's a 1060 coin cell battery. And that's a standard battery. The capacitor, I used a through-hole capacitor. So you see capacitor THT is a through-hole capacitor, and it is C disk, and it is 2.55. So I just searched for 2.55, and you would just research which footprints match your component, or you can do what I did when searching, is I would right click it and click view footprint, and I would zoom in and be like, all right, let me use the measuring tool to measure distance, and let's see how the distance is. It's 5 millimeters. That's about the size of my capacitors, and my wires bend on my capacitors, so I'm just going to assume that that's good. It's really not too big of a deal, so that's why I chose that one. So go ahead and paste all of those, and you can actually click Control C, and you can paste them by clicking each one and pressing Control V. Our display, we actually created a custom footprint. So if we go to the libraries, we can actually go down to IEEE at Mega 328p, and we have our custom footprints right here. So you can see that that's my custom LED clock display footprint. And if I view that, you can see that's the one I made. And also the micro USB breakout. I had the SIP-5, which is my 5-pin header, which I needed for the breakout. Okay, so transistors. And this is where I want to explain something very important about Ultra Librarian. It is a website that actually makes it very easy to find components. Sometimes you won't even have to design your own PCB footprints and schematic symbols because it exists already. So the reason I have to search that for the transistors is because you can see there is no such thing as transistors here, which seems kind of weird. I don't know why. Maybe I just can't find it. Um, so what I did was I actually found one online on Ultra Librarian. So as you can see here, this is a transistor I researched and they said it's good for switching, which is the purpose that I'm using it for. So if you go to ultralibrarian.com, you can actually search the component that you're looking for, and there might exist, for example, the component you're looking for, and it has the 3D model, it has a footprint, and it also has a symbol. So what I'm going to do is actually download this. I want the KiCAD file and also the 3D model file. So I go ahead and click download, and it will download. And I already downloaded this, and it's just a zip file, ul dash, and then whatever component you have. UL standing for Ultra Librarian. So as you can see in components, I actually have it downloaded already. So to actually import the component, what you want to do is, I'm just going to go ahead and save this so I don't lose my process. So you can open up the footprint editor, and then you can go to the library that you want to upload to. You can click the library, which mine is the IEEE AdMega Footprints, right click, and then you would click Import Footprint. Then you would navigate to wherever the footprint is, and for me it's right here, and it is in Components. And this is just the unzipped version of what I just downloaded in front of you. And in here you can click the KiCAD file, and then just keep going down until you see footprints.pretty, go into there, and then you have this file, which is a .kicad_mod file. Open that, and it will open your footprint. And as you can see, the solder mask here is very bad, so I'm just going to move this out of the way to make it more presentable to whoever is assembling the component. And then what I'm going to do is click Save As, add the component name, and I will go to my components and save it as in there. So now you can see under the IEEE AdMega Footprints, there exists this new file, which is the transistor. Okay, so that's good. So now what I can do is go here, and now there exists a new footprint, which is a transistor. And I will just copy this, and using the arrow keys, go down and copy it down. For the resistors, and I would skip this part, but unfortunately, I have to do it because that's part of the. Where is resistors? Oh, maybe I should just look at this. Resistor. Where exists? Okay, resistor through hole, and I have our axial dyno 207 and 6.3, 2.5, 7.62. 6.3, 2.5, 7.62. Just really quickly, and you would just research whichever resistor you would use, or you can go through, like I said, and you could just view the footprint and measure the distance to see if it would, fit your components. Now we have a button, so we have to go to button, which is on B, button, switch through hole, and that is 6 millimeters. So go down here, push 6 millimeters. So that's good. And I would just copy this down like that. These two are already assigned automatically once you place the component down. Now we need our 32.768 kilohertz crystal, so you come up here to crystal. And the crystal is a crystal DS15, D1 1.5 5.0, 1.5 5.0. Let's see, does that exist? 1.5 5.0, and I want the horizontal. Oh, horizontal. Yes, that's right. 1.5 horizontal. And you can see, you know, the resonator I had was approximately 5 millimeters tall. As you can see, this is about, you know, 6 something millimeters. So, you know, it's a good, actually, no, this is actually 5 millimeters, or 5 millimeters. So that works for me. So that's why I chose that. It was one of those like barrel resonators. So I chose that. And then we have our 16 megahertz crystal, which will actually be the clock for the microcontroller. So if I look at crystal, that is the resonator 2-pin, resonator 2-pin, W10 millimeters, 5 millimeters. So there's that. And if you view that footprint, you can see, you know, it's kind of like, you know, one of those, you know, it's shaped like this. I forgot what they're called. But what I needed was a distance that was around, you know, 5 millimeters between the two pins. So that's what I got, and that's why I chose that. So that should work just fine. So now we've selected all of our footprints, and we can save that. All right. And after you select all of your footprints, now we have to do the next step in the process, generate netlist. So we click generate netlist, and it'll kind of place it into the file that is your, you know, that stores your project. Or alternatively, you can, you know, navigate to any other place you want to share it or save the netlist. We're just going to keep the name default and click save. All right, and the next step is to edit symbol fields or generate bill of materials, blah, blah, blah. And then we have run PCB new. But what I like to do personally is go up here to Tools and click Update PCB from Schematic. So if you click that, it'll open up PCB new, and then it would say that it added all of our components. Then you would click Update PCB, click Close, and now you have all your components kind of attached to your mouse. So once you click, it'll place them down. So nice. So these are all our components. So let me go ahead and move this up here. So like I said, this is PCB new. It is very similar to, you know, to EE schema in some of the shortcuts, but there are, you know, a few different functions. So, you know, you know, there's some new shortcuts to learn. So if you press X, you can add a new track. If you press V, it adds a via, and what a via is, you know, these kind of like interconnections between layers. And I'll quickly show you that. So let me just have two components that are like touching. And it, you know, it's a little dependent on having a good CPU and stuff. So, all right. So, which components like touch each other? And a lot of these components aren't really touching. And it's kind of awkward, you know. Here, let me just move this up here. So there. Okay. So let's start talking about footprints. So you can press M to move item. You know, you know, press M and it moves the item. And that's similar. You can press G to drag the item, which I suppose it doesn't work. Yes, for some reason I can't get it to work. So just use M. It's a little different sometimes. You press R to rotate, as you can see. You can press F to flip it. L is to actually lock it to where you can't move it anymore. So if you press L, now I can't move this anymore. And it says, do you want to continue? And it's very nice if you don't want to actually mess up anything that you did. So I'm going to press L to actually unlock it again, and now I can move it again. So that's very useful. All right. So, you know, while you're actually doing the workshop, if you choose to, these are the shortcuts for that. And, you know, now we're just going to actually talk about some PCB best design practices. But before I actually do that, let me quickly go over PCB new and all the buttons, just so you know how to use it. So at the right here, you have select item, and that just selects an item, and you can move it by dragging it. Right here, you have highlight net, and that does the same exact thing as EE schema. So if I have two connections, let me just go ahead and add a trace on the copper layer, the top copper layer. If you do this, you can actually highlight the net. So that's how that works. Very similar to EE schema. Right here you have display local RASnet. So the local RASnet is actually all these lines, and it kind of tells you how everything connects. Let me go out of there. I don't know why this is a button. Doesn't seem like it should be a button. So I'm just going to skip that because it's really irrelevant. You have add footprints, and that just adds footprints. That's the same as pressing, add symbols in EE schema. Now you have a very important button. It's add traces, add root tracks. So that is essentially how it works. Is you would go to a pad, and if you press on it, everything that it should connect to is kind of highlighted. So you can like connect everything together. I shouldn't connect ground together because that's a best practice, not to connect ground with tracks, but instead to kind of use like like a whole layer. What's it called? Where is it? A plane, a power plane. So I'll talk about that in a bit. So there's tracks, and you can like do different layers. As you can see, I can connect, those together with it. Oh, and it replaces. That's cool. So yeah, these are the different layers. A via is, if you go here, you can actually press put a via, and that actually allows you to switch to a different layer like that. So that's how that's done. So that's vias. And then you have add filled zones. And this goes with what I said earlier, how best practices are to add a power plane. So a filled zone is essentially that. So if I click this button and click, I can actually choose ground as the net for it to be a filled zone. And if I press OK, I can cover the whole thing. I'm not being super precise because I'm just trying to go over everything really quickly. And as you can see, it fills the whole area with copper and connects all the grounds together by adding this connection right here. So that's a filled zone. And while you're working on the PCB and making changes, instead of deleting the whole filled zone, if you add a new ground, you can right click and actually unfill all, and it kind of has an outline, but it removes a connection. So if you add a new component that has a ground, you unfill it and then right click it, and then you can actually fill it again. And also it actually helps with working on it. So if you unfill the zones, now it's easier to work with. So that's that. So that's a ground layer, and now I actually kind of want a layer for the VCC. So if I click it, I can click VCC, and I will just kind of fill this the same way, and just kind of do that. So now you can see anything with VCC, if I can find anything. You can see VCC is connected to this plane. And the reason you use ground and power planes is because it, electricity will find the path of least resistance. So it improves the efficiency of distributing power between your components. And also it removes the need to have to like jerry chain all the grounds together. As you can see, I would have to go boop, boop, all the way like that. So that's that. And that's a best practice. Always do ground and power planes. So let's go ahead and just, by selecting the fill zone, I'm going to right click and actually unfill these for use. I'll just refill them later. All right. And you can also add a keep out area to stop people from putting components there. Stop yourself from putting components there. Now I can't like put layers or anything here. Don't put stuff there. Is essentially what that is. Then you have add graphic line, and that's the same thing as using like when you're making a PCB design. You can go to the various layers like the silk layer, and you can add a silk layer. I don't know, just a random shape. You can add a circle to the silk layer. I'm just making a nice little design. Maybe this guy is like really happy. Just a happy guy. And that's these tools. You can just add graphics. And actually, if you view the 3D viewer, you can see now my little graphic has been made. So that's that. All right. And you can add a graphic polygon as well to make like a whole shape that is like filled in. So now if I view 3D viewer, you can see now it's a filled in shape. So there's that. You can add text. Hello. You just place that there. And I'm doing this on the silk layer so that you can actually see the layer. The silk layer is the only the only thing that's actually shown on the board. There's also a back silk layer. So you have the front silk layer, and then you have the silk screen, and you have the back silk screen. So if I draw something here, I can say back. You can see it's backwards because it is now on the back. So if I go ahead and view the 3D viewer and turn it around, you can see now I have that on the back right there. So there's that. So there's text. You also have adding dimensions. That's irrelevant. If you want to research that, you can go to the KiCAD documentation. Add layer alignment target. These are just like complicated things that allow you to do more precise, PCB design stuff. So you can research that on the KiCAD documentation as well. You can delete items. You can place auxiliary axis origin, blah, blah, blah. These are more complex things as well. And that just helps you with like kind of lining things up and measuring things. You can set the origin point of the grid, or you can kind of go to the grid and have your own user grid. This is what I would do personally when making a more complex design. Is I would actually edit the user grid and do the same thing I did when making the custom component. So it's all based on millimeters. You can set the grid size, the origin, and things like that. And obviously you also have the measure distance tool, and that helps you with like measuring things out to make sure you did anything right. All right, so I believe that's all the components of PCB new. On the left you have like displaying polar coordinates and setting the units to different things like inches or millimeters. You can even change the cursor shape. And oh yeah, if you click right here, you can actually hide the rat's nest. So that's the thing that tells you the interconnection between all the nets. You can hide that by doing that. You can show your filled areas or not. And you could show the outlines of the filled areas to make it easier to work with it. And these are just kind of things that make it easier to actually work with it. All right. So now, let's see what else we have to do. Let's just talk about really quickly some PCB best practices. If I come here, let's see. So you have to try to keep trace lengths as short as you can. And so how you would do that is actually by moving all the components in a way to where the rat's nest, the lines between them are as small as they can be. And then what you can do is connect all the components together. And that just takes a lot of time and effort to like make sure if you can like minimize the distance between them all. And that's just moving them around, trial and error. Another best practice is use power planes when possible. Like I said, the VCC and ground power planes by using the add filled zones button. You got to locate related components next to each other, and that should be a no-brainer. But essentially, if three components are related to each other and they're around, they function in the same manner, they work to do the same thing. Like all these transistors, for example, or these two components, right? They're connected. Then you would locate them next to each other, and that also kind of goes with like making the traces as small as possible. And that's just best practice. Okay, so the The design rules check, that is, I said electrical rules check, but that's actually design rules check. Can I like edit that? Oh, I'm on the wrong layer. Let me go to explanatory drawings. Okay. Let me just change that to, where is it? Design rules check. All right. So try to do a design rules check, which is up here, as often as you can, and it'll tell you some very important things, like, hey, your zones are not filled in. Let me try to refill them. And it can tell you that, there's unconnected pads, and things like that. And also, if you have two components overlapping, and you perform one of these, it'll also tell you that, courtyards are overlapping or pads are too close. And that just kind of makes sure that it, keeps you following good design best practices. Based on, the clearance that you set in the board setup, like the clearance and the track width. Did I talk about this? I don't think I did. I'm just going to talk real quick about the board setup. So the board setup is basically related to the, kind of the settings that whatever PCB manufacturer you have gives you. So, for example, if there's a PCB manufacturer and they want the clearance to be no less than 0.3 millimeters, and the track width to be no less than 0.3 millimeters as well, then you would do that, and now it kind of changes the track width and the clearance. You can even change the size of the via, the size of the via drill. This is just the outer part of the via and the inner part, and these are irrelevant for now. And yeah, that's pretty much how you do that. So that's the board setup. Let's see, what else is there? So yeah, that's the design rules check. Try to do that as often as you can so that you make sure you're following good design rules. So use the silk screen to your advantage. The silk screen, which is this blue layer right here, the front silk screen or the back silk screen, they're meant to improve how easy it is to actually build this the PCB, to assemble it. And whoever's assembling it, it may be you or it may not. They want it to be easy for them to actually see it. So make sure the text fields are not overlapping. Like this, that makes it kind of hard for the assembler to know because these two things are now like over each other. If we go to 3D viewer, you can see, they're kind of overlapping, and it kind of causes ambiguity and confusion. So make the silk screen very easy for the assembler to understand. Don't overlap. Make sure you know which component the text fields go to and things like that. You can also add text and stuff. Like you can just go to the silk screen, add text, and you can say, "Do this thing when assembling," and that tells you, all right, now whoever's assembling will know that because it is, physically on the silk screen. Okay. And let's see what else is there. Keep polarized components pointed in the same direction. For example, if you have for example, these transistors, make them all pointed in the same direction. You wouldn't want to, have one transistor which is upside down and this one not upside down, because whoever's assembling may think that they're, all pointed in the same direction, and then they'll assemble it incorrectly. And that's a very bad thing. And also capacitors, if they're like if it's like an electrolytic capacitor, make sure they're all pointed in the same direction. So that just makes it easier to assemble. And make sure to follow good guidelines. Take thermals into account, and because say for example, if you have something that gets really hot, put a PCB on, and if you need to make room for not a PCB, a heat sink. Make room for the heat sink. Make sure that you can actually fit the heat sink on and have no components that are blocking it. And also, if you have something that is really high current, then perhaps you should increase the width of the track. For example, if I have that, and that is a very high current trace, if I go up here and press E, I can actually change the width to be larger, like 1 millimeter. And you can see now it's larger and can actually support a greater current. And there's one last bit here. So there's that. And finally, the most important thing, never make 90-degree angles. The first reason being, it looks very ugly. And actually, this is even worse. Like any sharp angle like that could cause issues in manufacturing. So when you're doing traces, I'm actually going to delete that because that is just horrific. When you're doing traces, make sure when you turn, you only turn ever by a maximum of 45 degrees. So if you need to make like a 2-point turn, you can like go, turn once and then turn twice, and now it's good because they're not a 90-degree angle instead of like doing a 90-degree angle like that. That would be bad. Don't do that. And also I noticed you can like change tracks easily by kind of overwriting it. So that's cool. You can override tracks. This, I don't want that to be big anymore. I just overrided it. That's cool. So yeah, make sure that all traces are, 45-degree angles, things like that. Where does this even go? Oh, that's only one thing. All right, and that's really all I have for best practices. And so as you design this, let me just quickly go over these again, these layers. So you have the front copper layer, which is where the front traces will be, the back copper layer, which is the back traces. So these two are on different layers. These are the adhesive layers, these are the solder paste layers, and these you don't have to worry about. The silkscreen, the front and back silkscreen, which I talked about. The solder mask, this, it kind of reduces, oxidation in the pads, so it kind of adds like that layer. And actually, the solder mask should be everything but these areas. I don't know if that's like a thing. These are just user drawings, and actually, it doesn't show up on the PCB design at all, but it is good for the designer to kind of make some notes. So this right here won't show up on the design at all. Then you have explanatory comments. Eco 1 and Eco 2, they don't do much of anything. The edge cuts, obviously, if you have an edge, this will tell, if you draw like a shape, then this will be like defined. This will define the edges of the PC, the edges of the PCB. So now if I click View 3D Viewer, you can see now this shape that I created, makes up that PCB. All right. Then you got a margin that's deprecated. That essentially says, components can't go past this point. But it's not really enforced, so it's kind of a visual thing for people if they want to like tell themselves, hey, I don't want to like put components past that point. Then they won't. And it, there's a chance it could, I think it might, put an error in the design rules check. Like if I put that there and then do a design rules check, continue, it doesn't. Well, I guess it's just a visual thing. All right. Then you have the courtyards, which are just component courtyards. So like I said, if a component overlaps with another component's courtyard, it'll throw an error in the design rules check. Then you have the front and back courtyards. And these right here are just, kind of descriptions of like how to assemble it. So that's all the layers. Really, the most important layers are the front and back copper, or however much copper layers you have. The silk screens, front and back. And the edge cuts is usually what you would use on a daily basis. So there's that. So now, as what you can do is kind of rearrange all of these, make all the traces, and let me just go ahead and leave this. And I can actually show you the finished design. So if I open this up, this right here is my finished design. The mounting holes, you can actually, place a mounting hole by clicking add footprint. It will load all the footprints, and then you would just search mounting hole. So I'm just going to stop that because that's taking forever. All right. So let me go ahead and actually hide the copper layers by pressing this button right here. The planes right here that are the power and ground planes. So I'm just going to hide those. All right. And as you can see, here's my finished design. Here's all the traces. Actually, what I want to do is actually unfill these because I feel like that would be a better way to show you. Zones, let me just unfill them. So here's my design. I did the best I could with trying to reduce the amount of traces. But what I noticed was I had to kind of make these buses over here that kind of connect to because everything connected to the microcontroller, so it was a little awkward. With the edge cut, I created this nice curve to make it look very nice, and I added the filled in zones. And on the silk screen, I actually added some text, which tells you the version number and the title. So after doing all this work, you can let me just re-add these, fill them all in. Oops. And you can just click View 3D Viewer. And here's my finished design. And when you actually want to export it to a manufacturer, you would actually go to JL, if you're using JLC PCB as the manufacturer, you would go here and it'll tell you how it's a fairly complex process for, uploading the files to JLC PCB. And it could be different for different manufacturers. So really, you have to kind of research that on your own. So there's that. Is there any questions in the chat? All right. I don't believe so. So, if you're watching this asynchronously, thank you for going through it. I hope you learned some valuable information. And the workshop is downloadable from the description. And you can just go through it and see what you can do. You can start on either section. You can even look at the final design, and just kind of play with it. But that's that. So thank you everyone for watching, and I hope you have a wonderful day.